Hello, good evening. Myself Ananya P. Mukherjee. I'm from Department of Earth Sciences, IIT Kanpur. So, I will be taking up the lecture on physics for class 12 chapters. And today we will be starting with the unit 1, that is the electrostatics part. So we will first start with understanding what is an electric charge. So we all are aware of the term electricity. Electricity is something that is very much, close to our day-to-day lives. We have a lot of, our daily work dependent on electricity, and that is why electricity is very important for us to study, so that we can, as we go ahead in our career in our future, we could contribute more in understanding, and also, try to understand the appliances, all the other applications of electricity. So before we go into electricity, we will first try to understand a phenomena, or the basic understanding of electrostatics. Okay, so electrostatics deals with the study of forces, fields and potentials that arise from static charges. What are static charges? Static in its own sense, it means about, like, it denotes something that does not move or change with time. Okay, so static means it's stationary, it is at one place itself. So electrostatics is going to be dealing with studying electric charges which are not moving in nature. Okay, so they are at a place. So the very big, very simple example of what is static electricity. I think most of us have, tried this experiment sometime or the other. Okay, so you take a plastic ruler and you take some of your hair, or you can just, just rub this against your hair. Okay, so if you are rubbing, okay, this rubbing itself is causing friction to, take place between the hair and the ruler. Okay, and because of this rubbing, some charges are getting transferred from the hair to your ruler. Okay, now to understand static electricity, we will see how this, after rubbing this, when you're getting, charging up your ruler, it is going to attract few pieces of papers. Okay, and with time it will start falling. Okay, the electricity, the nature, or the, kind of that phenomena where it was attracting, it will also dissipate. So this is a very good example of static electricity. Okay, you can find more examples like this when you rub a balloon on a piece of silk, and then you take it near the same pieces of paper, or you rub the balloon and you take it towards water flowing from a tap. You will see that there is a change in the direction of the flow of the tap. Either it will be attracted towards the balloon, or it will be, deflected, or it will move away from the balloon. Okay, so this attraction and repulsion, okay, these are also properties of the charges that two objects have. So with understanding electric charges, we will understand what is electricity. So electricity is actually derived from the electron word, that is a Greek word. Okay, that means amber. So in ancient times, they realized that striking two pieces of amber, they used to, cause some charging between them. Okay, amber, it attracts objects. Okay, so that is from where the term electricity has come. Okay, so the property of matter, atoms and molecules, these are determined by magnetic and electric forces that are present within these substances. Okay, matter, atoms and molecules. Matter and atoms and molecules, these make up almost the entire space, entire universe. Okay, so there are magnetic and electric forces present within these. So water charge, charge is a property associated with matter due to which it produces and experiences electric and magnetic effect. Okay, so charges are responsible for both electric and magnetic forces or effects that we see happening around us. There are also only two kinds of an entity called the electric charge. Okay, so this is a video which you can refer to later on with some more basic experiments. Okay, which will introduce you to static electricity. You can try them on your own to have a bit of experience yourself. So now that we know that there are two kinds of electrification. Okay, one is when charges repel and when the charges attract. Okay, what I showed over here. Okay, so you have seen that the plastic ruler, once it got charged because of the rubbing on the hair, it attracted the pieces of paper. Okay, similar manner, if you take a glass rod or take a glass rod and you try to put it next to the balloon won't, if both of them are charged. Okay, once they are charged and they are oppositely charged, okay, one is negatively charged, one is positively charged, you will see that they will not attract, they will start pushing further away from each other. Okay, so that is why we say like charges repel. So, okay, unlike charges attract each other. Sorry, the example with the balloon, I said the opposite. Both of them are charged with the like charges. Okay, if both of them are positively charged, then they will not attract each other. They will push away from each other. If they are oppositely charged, then only they will attract. So when the plastic ruler was charged with my hair, okay, it had one type of charge and the pieces of paper had another charge, or they were not charged at all. Okay, so it got attracted because they are different charges. So that is why, and the property which differentiates these two kinds of charges is the polarity of charge. So polarity means there is a negative polarity and positive polarity. Okay, so that is why we have two different kind of charges. If an object possesses an electric charge, it is said to be electrified or charged. When there is no charge, it is said to be electrically neutral. Okay, so when we charge a glass rod with silk, we say the glass rod is now charged. Okay, when we rub the balloon with wool or silk or any such fabric, we say the balloon is now charged or electrified. If there is no charge, then it is electrically neutral. Okay. So this which not every material that is found on earth would be like similar way in their similar in the way that they are electrified. Okay, some will allow passage of electricity and some do not allow passage of electricity. So the substances or the materials which readily allow the passage of electricity are called conductors. Okay, so they have electric charges which are free to move, okay, inside the material. They are free to move from one end of the material to the other end of material. Okay, so they will conduct electricity. So metal, earth, human bodies, we are examples of conductors. They say humans, our bodies are very good conductors of electricity. We will come further that how as being a conductor is bad for us itself, and also how we can avoid it. Okay, and the substances which offer high resistance in passage of electricity are called insulators. Okay, so these insulators would get charged. Okay, they will get charged, but the charges cannot travel through the material. They will stay located in one at one end only. So materials like porcelain, nylon, wood, okay, these offer high resistance to passage of electricity, and these are examples of insulators. So when some charge is transferred to a conductor, it readily gets distributed over the entire surface. Okay, as I said, like from one end, if it is getting charged, it will very easily distribute itself and it will easily pass through the entire material to the other end. But the opposite thing happens with the insulator. Okay, if one end is charged, it will stay at that one end only. The other end is not going to get charged in the same manner. Okay, so the process of sharing the charges with the earth is called grounding or earthing. Okay, this is what I was saying, that we as humans, we are also conductors. Okay, so we in a case where there is faulty current that is flowing through, say, your plug point or your appliance. Okay, so that we don't get the electricity does not pass through us, we there is something that is done, that is grounding or earthing. Okay, so this is a safety measure that is present for electrical circuits and appliances. So what is this grounding or earthing? Okay, so you can see in the diagram over here, there are two situations. In one where there is earthing is present, and the other where earthing is not present. Okay, so electric earthing is done by connecting the non-current equipment of the supply system to the ground. Okay, so we said there is grounding and earthing. Okay, so both of them are similar, but the grounding, okay, the grounded wire is not maybe connected to the actual earth, okay, but it is connected to a zero potential with respect to the other points of the circuit. Zero potential. Okay, you can see in the one there is no earthing over there. Okay, and the electric circuit, it is the anything that is passing through the electrical device. Okay, if there is a fault current which is there, okay, we will start conducting it and it will pass through, because we will complete the circuit then. But if the earthing is present, okay, we are not we will not experience any electrical shock. Okay, the fault current, it will flow through the earthing wire. Okay, it will flow through the grounded or the earthed wire, okay, back to the electrical circuit. It will not flow through us. So earthing is usually done for the buildings, the constructions. Okay, so buildings are the a flat plate is placed in the ground, so that if when lightning strikes maybe, so it will not it will just get the earthing wire is going to attract it, and it will flow directly to the earth without causing any issue or any fault in the construction itself. So that is earthing. And grounding is like earthing, but it is not connected to the ground actually, but it is connected to zero potential. Okay, so it can pass through that earthing wire, the grounded wire, and it will go to the electrical circuit itself. So now we understood what are electric charges. Okay, and we also understood that there are two kinds of charges. One is positive and negative. And then we also understood what are like charges and unlike charges. Okay, if there are two bodies which are charged, okay, if they both have the same polarity of the charges, that is, if they both have positive charges, then they will be called like charges. If one is positive and one is negative, it will be called they will be called unlike charges. Okay, and next we learned that unlike charges attract each other, like charges repel each other. Okay, so this is a basic understanding that we need to know. So how does a material get charged? Okay, so at any time, okay, a certain object, at least when we are talking about in the sense of static electricity or electrostatics, bodies are not charged. There are some bodies which are just kept, they are prone to get charged, but they do not hold the charge. If you take one material and just see it, okay, it has both positive and negative charges in it, okay, and they cancel each other out. Okay, so there is no polarity in between them, nothing. Okay, so now we will learn how charging, or how an object can get electrically charged by a phenomena or by a process called induction. Okay, so in this example over here, there are two metal spheres A and B. Okay, so and they're supported on insulating stands. So the whatever charge is there, it is going to stay in the spheres itself. It is not going to flow through the stands, and that's why we have insulating stands. Okay, so we have kept them on the stands and we have kept them close to each other. Okay, they are in contact, the spheres. So a positively charged rod is then brought near sphere A. You can see in the, so you can see, okay, the two spheres are in contact with each other. Okay, and then you bring a positively charged rod, okay, close to sphere A. Now since the glass rod, okay, the rod is positively charged, okay, so it will attract the opposite charges. Okay, so that is the negative charge. So as I said before, at first, you know, these two spheres have equal electrons and, you know, positive charges and negative charges on them. Okay, they cancel each other out and they are evenly distributed. Okay, they are all mixed over here. So there is no particular direction or, you know, any area where they are concentrated. But when you bring this rod, positively charged rod towards, you know, sphere A, since this is positively charged, all the negative charges are going to get attracted towards the side where the positive rod is there. Okay, and all the like charges, that is the positive charges, will get repelled. Okay, and they will go to the other end. Okay, over here. They will go to the other end since they are being repelled by these. Okay, in a short time, we will see that equilibrium is, you know, attained due to the attraction force, okay, force of attraction of the rod with the negatively charged, negative charges, and because of the force of repulsion due to the accumulated charge. See, you can see that, you know, over here all the positives will go on this side and all the negatives will be there. There will be an equilibrium situation, okay, that we will find in this. Okay, this is then called induction of charge. Okay, and this usually happens almost instantly. As soon as you bring it towards the sphere A, this is going to happen in an instant, in just a very short amount of time. Okay, then the accumulated charges, they remain on the surface, okay, until the time the glass rod is still held next to the sphere A. If we remove the rod, okay, the charges are then not, you know, there is no other force that is acting on these charges, okay, and then they go back to their original neutral state. Okay, because they are in contact, okay, they will start redistributing themselves in a state that they go back to the neutral position. Okay, now what we will do is that we will separate the spheres with a small distance. Okay, you can see over here that they are no more in contact with each other. There's a small distance between them. You again bring a positively charged glass rod, okay, next to sphere A, okay, and you will see that again the same thing happens, okay, that the surface near the positively charged rod is going to get negative charges over there, and on the other end, on the other surface of the sphere B, you will see positive charges. Okay, and slowly you will see that these two, all the negative charges, the negative charges are going to be accumulated here, the positive charges are going to be accumulated here. Okay, since now they are separated, all the positive charges from here are not going to be, okay, so there are charges here and there are charges here also. Okay, so this will also induce a force of attraction between the two spheres. Okay, now if we remove the rod, okay, the charges will rearrange themselves, okay, and now you will see that the negative charges have gone to the other side, because now over here we saw that they were the attracting forces are also, acting over here. Okay, now these have become negative, these have become positive, and now they are attracting each other. Now if we separate the spheres quite apart, okay, and the charges will now get evenly distributed over it. Okay, and now these two are charged. This is negatively charged and this is positively charged. Okay, so this process, okay, where the metal spheres now will be equal and oppositely charged, is called charging by induction. Okay, the rod has not lost any of its charge, okay, it has not transferred any charge from itself to the sphere, okay, but because of it being, just close to it, not even in contact, okay, the charge, the charging has been induced by the glass rod over here. So this is what we call charging by induction, and this is how most of the materials get charged. Okay, induction is a very important process by which some object would get electrically charged. So now we come to some properties of electric charge. Okay, there are some basic properties that are followed by the electric charge. The first one is the additivity of charges. Okay, charges can be added up like real numbers. So the total charge within a body can be presented as the algebraic sum of all singular charges that are acting on it. Okay, so charges are scalar in nature, and that's why they add up like real numbers. So suppose there are n charges, okay, so the total charge would be q1 plus q2 plus qn. Okay, so this is how charges can be added up and the total charge can be found of a system. Next is conservation of charges. Okay, so total charge of an isolated system is always conserved. Okay, that means the initial and the final charge of the system will be same. They might be distributed, okay, they might they might be polarized, but if there is some amount of charge, that amount of charge will stay same. Okay, so it is neither created nor destroyed. Charge cannot be created or destroyed. Okay, so it is conserved. So when objects get charged due to friction, there is a transfer of charge from one object to another, but the total charge of the system, okay, of both the objects and the transfer between them, the system is going to remain the same. Okay, so if it is getting transferred from one place to another, so whatever whatever one body has gained, okay, whatever charge that has been lost from the other body, so it's the total charge would be the same of the system. The next is the quantization of charge. Okay, so charges exist in discrete amount rather than continuous values. Okay, that is why we can quantize them. So this property states that the total charge of a body represents the integral multiple of a basic quantum of charge. Okay, so charge, you can give a quantity or to a charge. Okay, so we will learn in detail that an electron and a proton, okay, they have a certain quantity assigned to their charge. Okay, so that means a charge can be quantized. Okay, charges can be conserved and charges can be added. Okay, so these are some basic properties of electric charges. So as we said that an electric charge can be quantized. So Q is the charge on an object, okay, which is an integral multiple of its electronic charge. Okay, so by convention the charge on an electron is taken to be negative. Okay, that is why we have plus minus Ne over here. If you are considering electron, this will be minus Ne, and if you are considering positive, then it will be Ne. Okay, so charge on electron is written as minus E, okay, and on a proton it's plus E. So we know that any quantity, okay, we try to give it a unit. So the unit of the charge is Coulomb, okay, which is denoted by symbol C. Okay, so how do we define 1 Coulomb then? 1 Coulomb is the charge flowing through a wire in 1 second if the current is 1 ampere. Okay, so 1 Coulomb charge is said to be flowing through a wire in 1 second time if the current that is passing through that wire is 1 ampere. Okay, so E, this value, okay, this value is the basic unit of charge. Okay, and if we consider E as the basic unit of charge, putting the value of E in this equation, okay, that suppose we want to understand how many electrons are there in the charge of -1 coulomb. Okay, minus means it's electron. Okay, so putting this as Q and E, this value of E, we can find out how many electrons are there in the system. Okay, now see, you can see that this number, okay, this number is quite high. That's a lot of number of electrons, and charges of such large magnitudes are not really encountered in nature in like normal day-to-day life. So we actually consider smaller units, that is micro coulomb or millicoulomb. Okay, so that would be just micro would be your 10 raised to minus 6 coulomb, and milli will be 10 raised to minus 3 coulomb. Okay, so that is the unit of electric charge. Now we understood about electric charges, that is like the basic kind of unit which is giving rise to the phenomena of electricity and also magnetic effects. So we move on to how do we know, like we said that electricity it has the electric charges. Okay, there is a force of attraction, there is a force of repulsion which is acting between two charges. Okay, either they are like charges or unlike charges. So how are we going to denote this force that is there because of these positively or negatively charged particles? Okay, so suppose when the linear size of the charged body are much smaller than the distance separating them, okay, the size may be ignored and the charged bodies can be treated as point charges. Okay, so for our ease of computation of mathematical representation, okay, so we are going to consider something called point charges. Okay, so point charges are the distance between the charged bodies, okay, is much more than their linear size. Okay, so we are going to compute, or we are going to give the Coulomb's law for 2-point charges. So Coulomb measured the force between such 2-point charges, and he found that it varied inversely as the square of the distance between the charges and was directly proportional to the product of the magnitude of the two charges and acted along the line joining the two charges. Okay, so Coulomb said that the force, okay, that is acting, okay, force is inversely proportional, okay, inversely proportional to the square of the distance. Okay, we are going to consider r as the distance between the 2-point charges. Okay, so it is inversely proportional to the square of the distance, and it is directly proportional, okay, it is directly proportional to the product of the 2-point charges. So suppose you have q1 and then you have q2. Okay, so it is directly proportional to q1 into q2. Okay, so they are proportional. So to we take the a constant of proportionality, that is k. Okay, and then with that we give this formula, which is the Coulomb's law. Okay, so we say that the q1 and q2 are separated by a distance r in the vacuum. So the magnitude of the force between them is given by F is equals to k mod of y mod, because one could be minus. Okay, so we are taking the magnitude, so we are not going to consider the sign over here right now. So under mod we have q1 into q2 upon r square. Okay, so in SI units, the value of this constant of proportionality is K. Okay, so the K is 9 into 10 raised to 9 Newton meter square per Coulomb square. Okay, so if we have equal charges, okay, equal and same charges, okay, positive charges. Suppose Q1 and Q2 both are positive charges of 1 coulomb, and the distance between them is 1 meter. Okay, so putting these values and the K value in this Coulomb's law equation, we will find that the force is equals to 9 into 10 raised to 9 Newton. Okay, so this is the force that is acting upon two charges, okay, of 1 coulomb each, and the distance between the two charges is 1 meter. Okay, so we can infer from this is that 1 coulomb is the charge that when placed at a distance of 1 meter from another charge of the same magnitude in vacuum experiences an electrical force of repulsion of magnitude 9 into 10 raised to 9 Newton. Okay, repulsion, why? Because it's the same charge, same magnitude, okay, same sign. So these are like charges, and that is why they will experience a force of repulsion between them. So now we know that the K is a constant of proportionality, but it is also defined. Okay, it is defined as 1 by 4 pi epsilon 0. Okay, so that is why, okay, Coulomb's law is then written as F is equals to 1 by 4 pi epsilon 0 under mod Q1 into Q2 upon R square. Okay, so what is E0? It is the permittivity of free space. Okay, permittivity of free space, and in SI units the value of permittivity is 9 into 10 raised to minus 12. Okay, so suppose there are two charges over here. Okay, one you have Q1 and Q2. Okay, so if we want to now force is a vector quantity. Okay, even the force of repulsion or attraction that is experienced by two charges will also be a vector quantity. Okay, so that is why we have uh, this R21. Okay, this is the unit vector that is along the direction of the electric force acting on charge Q2, okay, because of the presence of charge of Q1. Okay, so then we will define Coulomb's force of law between 2 point charges Q1 and Q2 located at R1 and R2 respectively. Okay, so force experienced by Q2 due to Q1 is given by this formula. Okay, 1 by 4 pi epsilon square mod of Q1 Q2 by R21 the square, and this is the unit vector of the direction from Q1 to Q2. Okay, and similarly if force 1 2, that is the force on charge Q1 due to charge Q2 will be given by this formula. You see now there is a negative sign. Why negative sign? Because you see the direction has changed. Okay, the direction will be different from the force that is acting on Q1 due to Q2. Okay, so this is inverse, or this is the it is opposite, in the opposite sense. Okay, so this is how Coulomb introduced the the phenomena that there is a force of attraction or repulsion that exists between two charges, and how we can quantify it. Okay, now you can see over here that force again, we have seen that the force is going to be inversely proportional to the square of distance. So if this becomes larger and larger, the force is going to get weaker and weaker. Okay, so this is something we are going to look at at different stages while we are going to study electrostatics and current electricity and then magnetic effects. So Coulomb's law defined the force due to 2 point charges. Okay, now when we are considering a system, there are going to be a number of other charges. So since we all also saw that force, even electric force, okay, that is existing, is a vector quantity. So force on any charge due to a number of other charges is the vector sum of all the forces on that charge due to the other charges, okay, taken one at a time. The individual forces are unaffected due to the presence of other charges. Okay, so this you know kind of this principle, okay, it's called the principle of superposition, that any force that is experienced by this point due to the presence of the other charges, okay, is going to be a vector sum of all these charges, okay. It's the vector sum of the forces that is acting on this charge due to all the charges, okay, taken one at a time. So first, suppose we take q1 response, q1, okay, so we will calculate the force, okay, on q1 due to q2, q3, q4, say, okay, over here we have only q2 and q3, okay. So the force on q1 will be the vector sum of all the forces that is acting on q1, okay. So we will calculate F12 and F13. What is F12? F12 is the force acting on Q1 due to Q2, okay, and F13 is going to be the force of force on Q1 due to Q3, okay. So the total force that is acting on Q1, that will be F1, okay, will be the vector sum of F12 and F13, and this is called the principle of superposition. The principle of superposition says that in a system of charges, say from Q1, Q2 to Qn, the force on Q1 due to Q2 is the same as given by Coulomb's law, that it is unaffected by the presence of the other charges, okay. So the force that Q1 is experiencing due to Q2, okay, is going to be given by Coulomb's law, and this force is not going to be affected by, say, F13 or F14, F1n, okay. So this is not dependent on the other charges. The force that is acting on Q1 due to the presence of Q2 is not going to be affected by the other charges. So the total force F1 on the charge Q1 due to all other charges is then given by the vector sum. You can see over here F1 is equals to F12 plus F13 all the way till F1n. Okay, n can range from 1 to any number, and then by putting the Coulomb's law, okay, so you with Coulomb's law you find F12, F13 all the way till F1n, okay, then you add them up, okay, you see that the k, the proportion, the constant of proportionality k is going to be taken out as a common common term, and then you add all the other terms, okay. So this is your final equation, okay. So forces acting the force, the total force that is acting on one charge due to the other charges, due to the presence of the other charges, is the vector sum of all the force on that charge due to the other charges, okay. So you can see that you start, okay. So you have the Q1, okay, this is the charge that we are taking into consideration. At one time you take up one charge, okay, any charge. Now we want to understand the force that is acting on Q1, so we take that charge out as a constant, as a common term, and you have 4 pi epsilon 0, okay, that is also taken out, and then you do the summation of the other charges upon the distance, upon the square of the distance between the concerned charge and the other charges, okay. So this is a vector sum, okay. So based on this, now based on the Coulomb's law, we can solve this example. This is an example. So what is the force between two small charged spheres having charges 2 into 10 raised to minus 7 coulomb, and the other charge is 3 into 10 raised to minus 7 coulomb, okay, and they are placed 30 centimeters apart in air. In air means like in vacuum, okay. So we saw that Q1 is 2 into 10 raised to minus 7 coulomb, Q2 is 3 into 10 raised to minus 7 coulomb, okay. The distance 30 centimeters is given, so we convert this into meters, okay. So this is your Coulomb's law. This is your Coulomb's law. Okay, so we are going to find the force between the two charges using the Coulomb's law. This epsilon 0, this epsilon 0 is this value. Okay, so you put this value over here. You put 2 into you put 2 and 3 over here, and then you also do r square. Okay, so what is this going to give you? We'll just see that. Okay, and we also know that K is equals to what? Okay, if we consider the entire this proportionality thing, okay, we had found that K is equals to 9 into 10 raised to 9 Newton meter square per Coulomb square. Okay, so we know K, so F is equals to 9 into 10 raised to 9 into, so you have 2 into 10 raised to minus 7 and 3 into 10 raised to minus 7, okay, and then you divide this by 0.3 into 0.3, it is square, okay, 0.3 into 0.3, okay. So if you solve all of this, okay, so I'm just going to give you the answer to it, okay. So it is going to be 6 into 10 raised to minus 3 Newton, okay. So this is going to be your F, okay. So that is the force that is acting between the two charges. Now what kind of force will this be? We see that both of these are positive charges, okay, they are the same charges. So this is going to be a repulsive force, okay. So this will be a repulsive force of magnitude 6 into 10 raised to minus 3 Newton. Okay, so this is a very easy example for you to understand how to calculate the the force between two charged particles. Okay, now we will understand how the direction of the forces matter. Okay, the direction, the fact that whether they are like charges or unlike charges. Okay, so suppose you have 4 point charges. Okay, we first take the at the corners of a square ABCD of side 10 centimeters. What is the force on a charge of 1 microcoulomb placed at the center of the square? Okay, so we take this, suppose this is a square, okay, this is a square, you have A, okay, you have B, you have C, you have D, okay, and you join, okay, so suppose this is your 10 centimeter, okay, and now you have the charges. QA is 2 microcoulomb, okay, QB is minus 5, C is 2, okay, so C is again 2 and QD is minus 5, okay. So with the sides being 10, okay, and then you have a center, okay, suppose there's a charge of 1 over here, okay, so this is say the center, we consider it as O, okay, so AB is equals to BC is equals to CD is equals to AD is equals to 10 centimeter, okay. So now what will be the diagonals of it? AC is equals to BD okay, is equals to 10 into root 2, okay, centimeters. Okay, so once you have AC is equals to B is 10 raised to 2, 10 root 2 centimeters. Okay, what will be OA and OC, OD is equals to O is equals to OB is going to be 5 by root 2 centimeter. Okay, so now over here you can see that these two are same like they are like charges with the same magnitude. Okay, so there will be repulsive force, okay, from between A to C. Okay, so there will be in the same magnitude, the force between corner A and center O is also going to be the same in magnitude and sign as from corner C to A to O, sorry. Okay, so the force acting on point O, the charge that is situated at O, okay, due to charge A, and the force acting on O due to charge at C, they are going to be same in magnitude, okay, and they are going to be like charges, so there will be a repulsive charge. Okay, now if you consider between BO and D to O, okay, so the force on O, force on the charge at O, okay, due to charge at B, okay, is going to be same in magnitude, and it is going to be the same in magnitude even from when we consider the force on charge at O due to charge D. Okay, so they are also going to be the same. Okay, so you see even that is going to be a repulsive force. Okay, there is attraction between O and B, and there is attraction between O and D. Okay, so they will, it will start getting attracted to both sides. Okay, and over here it is going to be repulsive force. So actually these forces are, then acting in two different directions. Okay, so the net force actually on center is actually going to be 0, because the forces here are getting cancelled out by each other. Okay, so with this you can see that how the direction of the forces are also affecting the net force that is acting on a charge. Okay, so the entire solution I will put it, after the class, this will be shared. So the entire solution will be given over here. So which will help you to understand the influence of the direction and the magnitude of the charges on the net force. So now we will come to electric field. Okay, so we learned electric charges. We learned about the force that is, acting between two charges. Okay, either force of repulsion or force of attraction. Uh, Now we know that, multiple charges can all. First we learned the Coulomb's law, the force between 2 point charges. Then we learned that in a system, due to the presence of other charges, okay, the force acting on each charge is going to be, different, and it is related to the other charges that is present. So then we introduce the term electric field. Okay, so the word field signifies how some distributed quantity, scalar or vector, it will vary with position. Okay, so the charges, the presence of charges, okay, is going to produce an electric field. Okay, produce as in there is some kind of distribution, the distribution of the charges is going to have an effect. Okay, and due to their positions, this effect is going to be, there's going to be effect on the effect on the quantity or the forces that we have seen. Okay, so we know that by Coulomb's law, force between say charge Q or capital Q and on a charge Q will be given as 1 by 4 pi epsilon 0 Q into Q upon R square. R is the distance between the charges Q and Q. Okay, this is the charge on Q because of the charge on small q. Okay, now the charge Q will also exert an equal and opposite force on the charge Q. Okay, the electrostatic force between the charges Q and Q can be looked upon as an interaction between the two charges, okay, and the between charge Q and the electric field that is produced by Q, okay, and vice versa. So the force, okay, so the force that exists between the charges is actually the interaction between the charge Q, okay, and the electric field that is induced or that is developed due to the existence of charge Q. So if the position of charge small q is given by vector r, okay, so you introduce a unit vector r, okay, that is associated with the position of the charge q, it will experience a force F, okay, that is equal to the charge q multiplied by the electric field at the location q. Okay, so the force, okay, so the force that is experienced by the small charge q, okay, is going to be a multiple the multiplication product of the charge with its electrical field, okay, at the location of q. Similarly, the electric field, in similar manner we can find a force that is related to the charge big Q also. So that is why we say the electric field due to a charge Q at a point in space may be defined as the force that a unit positive charge would experience if placed at that point. Okay, so we place the small charge Q in the electric field that is due to Q, okay, and the field is thus field of charge Q, okay, field due to this charge is going to be defined as the force, okay, that the unit positive charge will experience because it is being placed at that point within the field that is developed due to the charge Q. So this is the electric field, okay, so that is the interaction between the electrostatic force that is experienced, electrostatic force that is experienced by a charge because it is being placed in at a location that is affected by the electric field of Q. Now this is due to the electric field due to say between two, where we are considering only 2-point charges. In a system of charges again, so we will have an electric field due to a system of charges too, where there are multiple charges, okay, that are present. You can see over here there is Q1, Q2, Q3, Q4. Okay, so again by Coulomb's law we find E1, that is the electric field at R due to Q1 at R1. Okay, so E1, this is the point P, okay, suppose we are considering this. So the electric field that is experienced, the E1, okay, at R, distance R, due to Q1 that is situated at R1, okay, so this is where, how we give it, okay. Coulomb's law is going to give you the force, and then you have the Q into the force, okay, electric field is equals to force into Q, or Q into F, I think. Sorry, the force is given as the multiplication product between Q and ER. Okay, so using this equation, okay, and using Coulomb's law we get the force, and then with this equation we are going to develop the equation of the electric field, okay, and where this is the unit vector in the direction from Q1 to point P, okay, where sorry, there should not be this unit vector sign over here. This is R1P distance between Q1 and P. Okay, so in the same manner we are going to find the other electric fields, okay, that is developed due to the other charges. So Similarly, we can say that for all fields where you can find E3, E4, En, okay, due to the charges Q3, Q4, Qn. Okay, so electric field due to the system of charges, we can see that, we can find the electric field due to each charge that is, situated at a certain distance from the point in the field where we are calculating the electric field. Okay, then again it's going to be a vector sum because due to the superposition principle. Okay, due to the superposition principle, then we can find the electric field E at R due to the system of charges. Okay, so it's going to be a vector sum, and again we can see it's a summation. So E is a vector quantity that varies from one point to another point in space, and it is determined from the positions of the source charges. Okay, so what is a source charge? Previously we saw over here. Okay, so Q is the source charge and small q is the test charge. Okay, so we are saying that since Q is the one which is producing the electric field, so big Q is going to be the source charge and small q is going to be the test charge. So similarly over here, okay, we are considering all these as the the field that is created by these source charges at P. Okay, so we are finding the electric field due to these source charges. So that is why E is a vector quantity that varies from one point to another. If you change the R, okay, from all the within the system, you can find E at different points, okay, and it will vary from one point to another point in space, and it is determined from the positions of the source charges. Okay, so for today we will do till electric field. In the next class we will move from from electric field, and we are going to introduce other terms as electric field lines, electric flux, electric dipole. Okay, and we are going to understand the concept of electric field, which is necessary for us to understand electricity and also its effects in terms of when we come into magnetism. So for today that's it. So thank you for joining today's class. We will see you in the next lecture.